Hello and welcome to this presentation of the STM32H5 Reset and Clock Controller, or RCC. The STM32H5 Reset and Clock Controller manages the system and peripheral clocks. STM32H5 microcontrollers embed 4 internal oscillators, 2 oscillators from an external crystal or resonator. Regarding the phase-locked loops, or PLLs, the STM32H56X and STM32H57X integrate these PLLs, while the STM32H503 only integrates 2 PLLs. Many peripherals have their own clock, independent of the system clock. The RCC also manages the various resets present in the device. The STM32H5 RCC provides high flexibility in the choice of clock sources, allowing the system designer to meet both power consumption and accuracy requirements. The numerous independent peripheral clocks allow a designer to adjust the system power consumption without impacting the communication baud rates, and also to keep some peripherals active in low power modes. The system clock can be derived from the high-speed internal 64 MHz RC oscillator, or HSI, from the high-speed external 4 to 50 MHz oscillator, or HSC, from the low-power oscillator, or CSI, or from the PLL1 PCK output of the PLL1. The AHB clock, called HCLK, is derived by dividing the system clock by a programmable prescaler. The APB clocks, called PCLK1, PCLK2, and PCLK3, are generated by dividing the AHB clock by programmable prescalers. The RTC clock is generated by the low-speed external 32.768 kHz oscillator, or LSC, the low-speed internal 32 kHz RC oscillator, or LSI, or the HAC divided by value in range 1 to 32. This selection cannot be modified without resetting the backup domain. The LSC can remain enabled in all low-power modes and in VBAT mode. The LSI can remain enabled in all modes except in VBAT modes. Various clocks can be output on I/O pads. 2 microcontroller clock output pins MCO, MCO1 and MCO2 are available. A clock source can be selected for each output. The low-speed clock output feature enables the external output of the LSI or LSC clock, which is driven into the low-speed output clock or LSCO pad. This output remains available in stop modes, but not in standby and VBAT mode. This slide describes the features of 5 oscillators. The high-speed external oscillator provides a safe crystal system clock. The HSC supports a 4 to 50 MHz external crystal or ceramic resonator, as well as an external source in bypass mode. A clock security system automatically detects an HSC failure. In this case, a non-maskable interrupt is generated, and a break input can be sent to the timers in order to put critical applications such as a motor control in a safe state. When an HAC failure is detected, the system clock is automatically switched to an internal oscillator, either HSI or CSI, so that the application software does not stop in the case of crystal failure. The high-speed internal oscillator is a 64 MHz RC oscillator, which provides fast wake-up times. The HSI is trimmed during production testing and can also be user-trimmed to take into account temperature and voltage variations. The HSI can be automatically awoken when exiting any stop mode in order to make it available for peripherals when it's not used as the system clock. The HSI is used as system clock source after startup from reset, configured at 32 MHz. The HSI48 is generated from an internal 48 MHz RC oscillator. 48 MHz is a canonical frequency for a USB module. HSI48 can also be used as the reference clock for the RNG. The HSI48 is associated with a special clock recovery system, or CRS, circuitry that dynamically adjusts the frequency according to the receipt of a USB starter frame packet or the LSC or an external signal. The low-speed internal or LSI oscillator is the unique clock of the independent watchdog and can be the clock of the RTC. It can be kept running in all stop and standby modes. The clock frequency is 32 kHz. This table summarizes the features of the HSI oscillator. The values come from the STM32H5XX datasheets. Minimum, typical, and maximum frequencies are indicated for operation at 30 degrees Celsius. Startup time and stabilization time are also indicated. Note that the HSI has a faster startup time than the HAC crystal oscillator. Finally, the table provides the typical and maximum consumption of the HSI, knowing that the HSI can be switched off during the HSI on bit. The high-speed internal oscillator, or HSI, is a 64 MHz RC oscillator which provides fast wake-up times. The HSI is trimmed during production testing and can also be user-trimmed. A dedicated divider can generate 32, 16, or 8 MHz clock. The HSI can be selected as a clock at wake-up from system stop and as the backup clock if an HAC failure is detected by the clock security system. The HSI can remain powered when the system goes to stop mode in order to speed up the wake-up time. Certain peripherals, such as the I2CS and UART or LPUART, can request the activation of the HSI in system stop mode in order to generate wake-up events. The HSI is enabled by the peripheral only for the wake-up sequence detection and remains disabled outside of this wake-up sequence. The low-power internal oscillator, or CSI, is a 4 MHz RC oscillator which provides fast wake-up times. The CSI is trimmed during production testing and can also be user-trimmed. The CSI can be selected as a clock at wake-up from system stop. The CSI can remain powered when the system goes to stop mode in order to speed up the wake-up time. Certain peripherals, such as the I2CS and UART or LPUART, can request the activation of the CSI in system stop mode in order to generate wake-up events. The CSI is enabled by the peripheral only for the wake-up sequence detection and remains disabled outside of this wake-up sequence. This table summarizes the features of the CSI oscillator. Minimum, typical, and maximum frequency values are indicated for operation at 30 degrees Celsius. Note the power consumption, more than 10% lower than the one of HSI. For STM32H562, H563, and H573 devices, 3 PLLs integrated in the RCC are completely independent. Only 2 PLLs are available for STM32H503 devices. They offer the following features: AVCO supporting 2 modes, a wide range and a low range, used, for instance, in audio application cases. The input frequency is between 2 and 16 MHz for the VCO in wide range mode. The input frequency is between 1 and 2 MHz for the VCO in low range mode. The PLLs also provide 3 different outputs, which are all derived from the VCO output via post dividers: div-P, div-Q, and div-R. In addition, it's possible to change the values of the post divider without disabling the PLLs. The application just needs to disable the corresponding post divider. The 13-bit sigma delta modulator fine-tunes the VCO frequency in steps of 11 to 0.3 ppm. The sigma delta modulator can be updated on the fly without generating frequency overshoots on PLL outputs. This table indicates the maximum frequencies according to the voltage scaling ranges. In voltage range 0, the maximum performance is obtained, 250 MHz system clock. In voltage range 1 and 2, the maximum system frequency is respectively 200 and 150 MHz. In voltage range 3, the maximum frequency is 100 MHz. In all cases, the PLL output, before being divided, can be maximum 420 MHz. The LSC clock is generated from a 32.768 kHz crystal or ceramic resonator. It has the advantage to provide a low-power, highly accurate clock source to the real-time clock, or RTC, for clock and calendar or other timing functions. The LSC also offers a programmable driving capability, which can be used to modulate the amplifier driving capability. 3 modes are available: medium-low drive, medium-high drive, and highest drive. In case of an analog clock, the LSC by P and LSC on bits must be set to 1. In case of a digital clock, the LSC by P and the LSC X bits must be set to 1, followed by setting the LSC on bit to 1. The peripherals that can be clocked by the LSC are the USARTs, the UARTs, the low-power UART1, the RTC, the RNG, the HDMI CEC, the Cortex system timer, and the DAC1. A clock security system monitors for failure of the LSC oscillator. It detects a missing clock or over frequency. The CSS on LSC works in all modes including VBAT. It's also functional during system reset, excluding power on reset. The CSS on LSC failure is connected to a temper event. In the case of a failure, the application can switch the RTC clock to the LSI. This is not automatic. The temper flag must be cleared prior to accessing the secrets protected by this temper. Thank you for having attended this presentation. For more details, please refer to application note AN2867, which is an oscillator design guide for STM8S, STM8A, and STM32 microcontrollers.